Faster-than-light travel has long been a dream of humanity, a tantalizing prospect that could unlock the mysteries of the universe. But what does it really mean to travel faster than light? And is it even possible? Let's dive into the science behind this fascinating concept. For over a century, our understanding of the universe has been shaped by the work of one man, Albert Einstein. In 1905, this brilliant physicist revolutionized science with his special theory of relativity, a groundbreaking framework that introduced the world to concepts like space-time and the ultimate speed limit, the speed of light. This isn't just a number, it's a cosmic constant, clocking in at an astonishing 299,792 kilometers per second. But what makes this speed so fundamental to the fabric of reality? Einstein's theory revealed a profound truth about the universe. As an object accelerates, it gains mass. The closer it gets to the speed of light, the more energy it takes to keep accelerating, until, at light speed, it would require infinite energy. This energy barrier is not just theoretical, it has been proven time and again through experiments at facilities like CERN's Large Hadron Collider, where scientists accelerate particles to nearly the speed of light. Despite enormous amounts of energy, these particles can only approach, never reach, that ultimate limit. The speed of light also governs how time and space behave. As you approach light speed, time slows down and distances contract, a phenomenon known as time dilation. It's a reality confirmed by precise measurements such as those involving GPS satellites, which must account for time moving slightly slower in orbit compared to Earth. So why does this matter? Because this limit defines the universe as we know it. It means the vast distances between stars. Light years are more than just a poetic term, they're a physical reality. Even the closest star system, Proxima Centauri, is 4.24 light-years away. At our current fastest speeds, it would take tens of thousands of years to get there. The vastness of space isn't just intimidating. It's practically insurmountable. But humans are nothing if not ambitious. For centuries, we've looked up at the stars and asked, what if? What if the speed of light isn't the end, but a challenge to overcome? Could there be ways to move faster than light? Not by breaking Einstein's rules, but by bending them? These are not just fanciful ideas. They're the foundation of serious scientific theories. As we step into the next chapter, we'll explore how physicists are working to reimagine the nature of travel itself. By manipulating space-time, they hope to sidestep the barriers imposed by light speed and open the door to a future where interstellar journeys might be measured in weeks, not millennia. Einstein's theory of relativity tells us that nothing can travel faster than the speed of light. But what if we didn't need to? What if, instead of moving through space, we could move space itself? This idea lies at the heart of one of the most fascinating theoretical breakthroughs in modern physics, the warp drive. In 1994, physicist Miguel Alcubierre proposed a model that could theoretically allow faster-than-light travel without violating the laws of physics. The concept is simple to describe, but staggeringly complex in practice. A spacecraft would remain stationary within a warp bubble, while the bubble itself contracts space-time in front and expands it behind, effectively carrying the ship forward. Within the bubble, the craft doesn't technically move faster than light relative to its local space-time, allowing it to sidestep Einstein's speed limit. But there's a catch. Several, actually. Early calculations showed that creating such a warp bubble would require exotic matter, a hypothetical form of matter with negative energy density. This type of matter has never been observed in nature, making it a significant obstacle. Moreover, the energy required to generate a warp bubble was initially estimated to be equivalent to the mass energy of Jupiter, a figure so astronomical it rendered the idea purely speculative. Then, in 2021, physicist Erik Lentz introduced a stunning refinement. His model replaced exotic matter with solitons, stable, localized waves that can maintain their shape while traveling. This breakthrough theoretically eliminates the need for exotic matter, though the energy demands remain immense. While Lentz's work is still far from practical application, it represents a critical step forward, showing that warp drives might not be as impossible as once thought. Another bold idea is the concept of wormholes. Originally theorized by Einstein and physicist Nathan Rosen in 1935, these Einstein-Rosen bridges are tunnels through space-time that could connect two distant points. Imagine entering a wormhole on Earth and emerging near Proxima Centauri moments later. The equations that describe wormholes are mathematically sound, but their practical application is another story. To keep a wormhole open and traversable, scientists believe it would require exotic matter to stabilize against collapse. Without it, the tunnel would snap shut in an instant. Even if stabilization were possible, wormholes raise profound questions about causality and paradoxes, challenges that remain unresolved. And then there are tachyons, hypothetical particles that always move faster than light. While intriguing, tachyons remain purely theoretical, with no experimental evidence for their existence. If real, they could upend our understanding of causality, as their superluminal speeds might allow information to be received before it is sent. A concept that defies common sense and raises questions about the nature of time itself. Among these theories, one unexpected breakthrough has added a surprising twist to the story. In late 2020, physicist Harold Sunnywhite and his team observed what appeared to be a nanoscale warp bubble during a Casimir cavity experiment. This was a serendipitous discovery unrelated to FTL research, yet it suggests that the formation of warp bubbles might be physically possible, even if only at quantum scales. While far from practical, this finding provides a tantalizing hint that these theoretical ideas might have a basis in reality. The beauty of these concepts, warp drives, wormholes, and tachyons is that they challenge us to rethink the universe's most fundamental rules. They blur the line between science fiction and science, offering a glimpse of what might be possible in the distant future. But they also raise profound questions. How do we overcome the energy barriers? Can exotic matter ever be created or discovered? And how do we navigate the ethical and existential challenges of manipulating space-time? In the next chapter, we'll tackle these challenges head-on. The road to faster-than-light travel isn't just a technological problem, it's a journey that forces us to confront the very nature of reality itself. The pursuit of faster-than-light travel has inspired some of the most imaginative theories in physics. While rooted in rigorous mathematics, these concepts push the boundaries of what we consider possible. They explore mechanisms that could allow us to traverse vast distances in the cosmos, not by accelerating faster than light, but by circumventing the limitations imposed by relativity. One of the most compelling ideas is the warp drive, first proposed by Miguel Alcubierre in 1994. Building on Einstein's equations, Alcubierre's concept suggests that a spacecraft could remain stationary within a warp bubble while space-time itself moves around it. By contracting space-time in front of the bubble and expanding it behind, the ship could effectively travel faster than light relative to an outside observer. This innovation allows the craft to sidestep the light speed barrier without violating relativity, as it never moves faster than light within its local space-time. However, creating a warp bubble remains a monumental challenge. Alcubierre's original model required exotic matter with negative energy density to stabilize the bubble, a substance that has yet to be observed in nature. Additionally, the energy demands were estimated to be astronomical, equivalent to converting the entire mass of Jupiter into energy. These barriers rendered the warp drive little more than a mathematical curiosity, until recently. In 2021, physicist Erik Lentz introduced a groundbreaking refinement to Alcubierre's model. His work proposed using solitons, stable energy waves that maintain their shape and structure, to create a warp bubble without the need for exotic matter. While Lentz's model significantly reduces some of the theoretical hurdles, the energy demands remain staggering, still far beyond anything humanity can currently achieve. But the significance of this refinement cannot be overstated. It marks a critical step forward in transforming warp drives from pure speculation to a concept worthy of experimental consideration. Another theoretical avenue involves wormholes, also known as Einstein-Rosen bridges. First described by Albert Einstein and Nathan Rosen in 1935, wormholes are hypothetical tunnels through space-time that could connect two distant points. Unlike warp drives, which manipulate space-time around a craft, wormholes would allow instantaneous travel between two regions of the universe. However, traversable wormholes come with significant challenges. To remain open, they would require exotic matter to counteract the gravitational forces that would otherwise collapse them. Even if this stabilization were achieved, wormholes introduce complex questions about causality, such as the possibility of time travel and paradoxes. Then there are tachyons, hypothetical particles that always move faster than light. Tachyons arise naturally in certain solutions to Einstein's equations, but their existence remains purely theoretical. If they were found to exist, tachyons could revolutionize communication and physics by allowing information to travel instantaneously across vast distances. However, their superluminal nature challenges our understanding of causality and could create scenarios where effects precede causes, an idea that defies our intuitive understanding of time. Amid these theoretical frameworks, one recent discovery has added an intriguing twist to the story. In 2020, physicist Harold Sonny White reported observing a structure resembling a warp bubble at the nanoscale during a Casimir cavity experiment. This finding wasn't directly related to FTL research, but it suggests that the formation of warp bubbles might be possible in certain physical conditions. While the observed phenomenon is far too small to be of practical use, it offers a tantalizing hint that these theoretical constructs could one day become real. Each of these concepts, warp drives, wormholes, and tachyons, offers a different path toward faster-than-light travel. But they all share a common thread. They challenge our understanding of space-time and demand solutions to immense scientific and engineering challenges. Yet even as they push the boundaries of physics, these theories force us to confront deeper questions. What would it mean to manipulate space-time? Could we ever harness the energies required? And are we prepared for the philosophical and ethical dilemmas that would arise from such advances? These questions lead us to the heart of the matter, the practical challenges and limitations that stand in the way of turning these bold theories into reality. In the next chapter, we'll explore the immense hurdles that humanity must overcome before we can hope to break the cosmic speed limit. And for all its allure, faster-than-light travel presents challenges that are as profound as the concept itself. These aren't just technical hurdles. They strike at the heart of our understanding of the universe, testing the limits of physics, engineering, and our ethical frameworks. The most immediate challenge lies in energy requirements. Theoretical models like the Alcubierre drive demand energy levels far beyond anything humanity has ever produced. Early estimates suggested that creating a warp bubble would require converting the entire mass of Jupiter into energy, a figure so vast it's almost incomprehensible. Even Erik Lentz's soliton-based refinement, which eliminates the need for exotic matter, still requires energy on a scale that dwarfs our current capabilities. To contextualize, even if we harness the output of every power plant on Earth for thousands of years, it wouldn't be enough. One possible solution is fusion power, a technology that mimics the energy production of stars. Fusion reactors, if perfected, could provide the immense power needed for FTL experiment. Beyond fusion, the concept of a Dyson sphere, a hypothetical megastructure designed to capture the energy of an entire star, offers another tantalizing possibility. While both ideas remain in development or speculation, they highlight the scale of innovation required to make FTL travel feasible. The second major challenge is material science. Any spacecraft designed for FTL travel would need to withstand extreme forces, gravitational distortions, and high-energy environments. Current materials would disintegrate under these conditions, requiring breakthroughs in nanotechnology and metamaterials. Scientists are already exploring materials with extraordinary strength and resilience, but these advances are still in their infancy. Then there's the issue of causality, the principle that cause precedes effect. Faster-than-light travel risks violating this fundamental rule of physics. For instance, certain FTL scenarios like traversable wormholes could create time loops or paradoxes, situations where an event occurs before its cause. While some models, such as the Alcubierre drive, attempt to preserve local causality, the broader implications remain a matter of intense debate. Another critical limitation is stability. Wormholes, for example, are prone to collapse without the presence of exotic matter, and even a momentary lapse in stability could destroy anything attempting to traverse them. Similarly, warp bubbles could be susceptible to quantum instabilities, creating unpredictable and potentially catastrophic outcomes. Finally, there's the question of control and precision. Manipulating spacetime requires a level of computational power and precision that far exceeds current technology. Advanced artificial intelligence and quantum computing may one day solve these problems, but they remain theoretical solutions for now. Beyond these technical challenges lie profound ethical questions. Who decides how FTL technology is used? Could it be weaponized? And how do we prevent it from deepening existing inequalities, allowing only the wealthy or powerful to access the stars? History is filled with examples of transformative technologies that have been misused or unequally distributed, and the stakes for FTL travel are even higher. These challenges are immense, but they are also part of what makes faster-than-light travel such a compelling goal. They force us to think not just about the technology itself, but about the kind of future we want to create. As we move forward, these questions will define the journey as much as the destination. In the next chapter, we'll explore what faster-than-light travel could mean for humanity, how it could transform our society, our understanding of the universe, and our place within it. Faster-than-light travel is not just a technological ambition. It represents a transformative leap that could redefine our place in the universe. If realized, it would revolutionize exploration, reshape human society, and challenge our understanding of existence. But with such promise comes profound implications, both practical and philosophical, that humanity must grapple with before venturing into the cosmos at superluminal speeds. At its core, FTL travel would make interstellar exploration a reality. The closest star system, Proxima Centauri, is 4.24 light-years away. At current speeds, even the fastest spacecraft would take over 70,000 years to reach it. FTL travel could reduce that journey to a matter of weeks. The ability to traverse these distances would fundamentally shift our approach to space exploration. Planets orbiting distant stars, such as Proxima b, a potentially habitable exoplanet, would no longer be mere objects of study but tangible destinations. Entire star systems could be explored within human lifetimes. But faster-than-light travel would also confront us with one of the greatest mysteries of existence, the Fermi paradox. If the universe is so vast and the probability of extraterrestrial life so high, why haven't we found any evidence of advanced civilizations? FTL travel could provide new answers to this paradox. Perhaps other civilizations exist, but they've chosen not to contact us, or maybe they've self-destructed before achieving interstellar capabilities. Equally possible is that life is far rarer than we imagine. Each of these scenarios would have profound implications for humanity's sense of purpose and uniqueness. The potential discovery of alien life raises ethical and philosophical questions that humanity has never had to address. What happens if we find intelligent life? How do we communicate with a species that might not share our biology, language, or perception of reality? And what moral obligations would we have in such an encounter? History provides sobering parallels. When technologically advanced civilizations encountered less advanced ones on Earth, the results were often catastrophic for the latter. How do we ensure that humanity's exploration of the cosmos doesn't repeat these mistakes on an interstellar scale? FTL travel wouldn't just affect our relationship with the universe. It would fundamentally alter life on Earth. The vastness of space has always been a barrier that shaped human society. Distance has defined borders, economies, and even cultural identities. But if space becomes easily traversable, how would that reshape our world? Would nations and corporations compete for control of the stars, or could humanity unite in a shared vision of exploration? The answers to these questions could determine whether FTL travel leads to a golden age or new forms of inequality and conflict. Even the act of manipulating space-time itself comes with unforeseen risks. Warp drives, wormholes, and other FTL mechanisms could create unintended consequences such as destabilizing local space-time or introducing gravitational anomalies that affect nearby planets. These risks are not hypothetical, they're inherent to any attempt to manipulate the fundamental fabric of the universe. Understanding and mitigating these dangers will be as critical as achieving FTL travel itself. And then there's the issue of access and inequality. Technologies of this scale would require immense resources, potentially exacerbating global disparities. If FTL travel becomes accessible only to the wealthy or powerful, it could create a new form of cosmic colonialism, where interstellar exploration benefits only a privileged few. Ensuring that the benefits of this technology are shared equitably will require unprecedented global cooperation. The stakes couldn't be higher. Faster-than-light travel isn't just a technical challenge, it's an existential one. It forces us to confront questions about who we are, what we value, and what kind of future we want to create. It could make the universe feel smaller and more connected, but it could also expose humanity to dangers and dilemmas we've never faced before. In the next chapter, we'll look ahead to what comes next. The research, technologies, and global efforts that could bring faster-than-light travel from theory to reality. The dream of faster-than-light travel is no longer confined to the realm of science fiction. While still theoretical, recent breakthroughs have brought the concept closer to reality than ever before. But where do we go from here? Achieving FTL travel will require unprecedented advancements in physics, engineering, and global collaboration, as well as a willingness to confront the profound ethical and existential challenges it presents. The first step lies in advancing the theoretical models. The Alcubierre drive remains a leading contender, and physicists like Erik Lentz are refining the concept to make it more feasible. His soliton-based warp bubble eliminates the need for exotic matter, a critical breakthrough. But the energy demands are still astronomical. Future research must focus on reducing these requirements. Recent studies suggest that certain configurations of space-time manipulation could significantly lower energy thresholds, but these ideas remain speculative. Beyond warp drives, wormhole research continues to evolve. Physicists like Kip Thorne are exploring ways to stabilize wormholes using quantum effects or theoretical exotic matter. While practical applications are likely decades or centuries away, these efforts are expanding our understanding of space-time and its potential for interstellar travel. Experimentally, there are glimmers of hope. Harold Sunny White's accidental discovery of a nanoscale warp bubble in 2020 suggests that the theoretical concepts behind FTL travel might have real-world implications. While this finding is far from proving the feasibility of warp drives, it provides a crucial foothold for future experiments. Energy generation is another critical frontier. FTL travel requires energy on an unprecedented scale, far beyond what current technologies can provide. Fusion power, which replicates the energy production of stars, is one of the most promising solutions. Meanwhile, the concept of Dyson spheres, megastructures that could capture the entire energy output of a star, offers a long-term vision for powering interstellar travel. These technologies, while still in development, are essential stepping stones. Artificial intelligence and quantum computing will also play vital roles. AI is already being used to simulate complex space-time geometries and optimize energy configurations for propulsion systems. Quantum computing, with its ability to process massive amounts of data simultaneously, could accelerate breakthroughs in FTL research from material design to navigation systems. However, the path to FTL travel isn't just technological, it's global. The development and use of this technology will require unprecedented international cooperation. Organizations like the United Nations Office for Outer Space Affairs, UNOOSA, and frameworks like the Outer Space Treaty of 1967 provide a starting point for regulating interstellar exploration. But as we move closer to achieving FTL travel, new agreements will be needed to address the ethical, legal, and geopolitical challenges it presents. Perhaps the greatest challenge is maintaining perspective. The journey to faster-than-light travel will be long, filled with setbacks and uncertainties. But humanity has faced seemingly insurmountable challenges before. Crossing oceans, landing on the moon, sequencing the human genome. Each of these achievements once seemed impossible, but they became reality through determination, collaboration, and ingenuity. Faster-than-light travel may take decades or centuries to achieve, but every step forward, whether it's refining a warp bubble, stabilizing a wormhole, or building a fusion reactor, brings us closer to the stars. And along the way, we'll gain a deeper understanding of the universe and our place within it. As we look ahead, the question is not just whether we can achieve faster-than-light travel, but what kind of future we want to build with it. Will we use this technology to unite humanity or to deepen divisions? Will we explore responsibly, or will we repeat the mistakes of the past? These are the questions that will define the journey, not just to the stars, but to a more profound understanding of ourselves.